if a function is not continuous, its derivative can't possibly exist. That is the big takeaway. Because what we can then say is, now you know that derivative doesn't exist when left-hand and right-hand slopes aren't equal. When you have a function that does something like the great school bird that you would draw, you know that at the corner where that bird meets, like at the base of that bird, the right-hand slope and the left-hand slope are not equal, so the derivative doesn't exist there. But what we've said now in this statement is something more. We said not only does the derivative not exist at points where left-hand and right-hand slope aren't equal, but the derivative also can't possibly exist where the function is not continuous. So if you're ever asked to look at a function and state where the function's derivative doesn't exist, you can look for corners along the graph of the function where the left-hand and right-hand slope are not equal. But you also can look at where the function is not continuous. And in fact, you also must look at where the function is not continuous. So the derivative can't possibly exist when the function's not continuous or when you have a corner. So as an example, to see this sort of in full totality, let's just imagine a function. Let's consider the following, and let me draw you up a graph. So let's imagine this graph has an asymptote. Let's imagine it's got a hole. Let's imagine it also has a corner. If we want to find where this function is non-differentiable, if we want to find where this function doesn't have a derivative, you know, first off, this corner is going to be an issue. So wherever this point is, maybe it's over at x equals 5. X equals 5, derivative can't possibly exist. Why? Left-hand slope, right-hand slope, not equal. There's a corner there. It's not, the derivative, which is a limit, can't possibly exist because the left-hand slope and the right-hand slope not equal. But x equals 5 is not the only point where the function does not have a derivative. The function also could possibly have a derivative when the function wasn't continuous. Because we worked through the logic to show that if you have a derivative, then you must be continuous. So if you're not continuous, you couldn't possibly have a derivative. And that would be like here. Maybe this is the point x equals 2. Or here at the asymptote where your x equals minus 4, let's say. But the long story short is, if you want to know where the function doesn't have a derivative, look for the holes, look for the jumps, look for the asymptotes, and look for the corners. The holes, jumps, and the asymptotes are where the function isn't continuous, because if the function's not continuous, you couldn't possibly have a derivative. And then the corners are where the left-hand slope and right-hand slope are not equal. So where does the function not have a derivative? Holes, jumps, asymptotes, corners. That's it.